Here's an octal-based ice cube relay inside the base. The ohmmeter indicates the coil has a resistance just shy of 1.7 kiloohms. If this coil was shorted, opened, or damaged, it would indicate a different resistance or show visible signs of abuse upon inspection. When in its deactivated state, the ohmmeter indicates there is a connection between the common and the normally closed side as expected. When manually triggered using the button on the front, the ohmmeter indicates the normally closed switch has opened. When in its deactivated state, the ohmmeter indicates there is no connection between the common and the normally open side as expected. When manually triggered using the button on the front, the ohmmeter indicates the normally open switch has closed. Ice cube relays sometimes feature an indicator LED on the face to facilitate troubleshooting a dimly lit or cramped electrical cabinet. Additionally, sometimes the manual trigger button or tab can be locked into place to facilitate troubleshooting or force an input. Here's a mini contactor relay. The ohmmeter indicates the coil has a resistance just shy of 380 ohms. If this coil was shorted, opened, or damaged, it would indicate a different resistance or show visible signs of abuse upon inspection. When in its deactivated state, the ohmmeter indicates there is no connection between the 1-3 and 1-4 terminals of the first normally open switch as expected. When manually triggered using the plunger on the front, the ohmmeter indicates the normally open switch has closed. When in its deactivated state, the ohmmeter indicates there is connection between the 2-1 and 2-2 terminals of the second normally closed switch as expected. When manually triggered using the plunger on the front, the ohmmeter indicates the normally closed switch has opened. Similar to their big brother, the contactor, mini contactor relays sometimes feature an access port on the side to allow a mechanical interlock between two relays in close physical proximity. The mechanical interlock may be as simple as a plastic peg or as complicated as a separate interlock unit that prevents the travel of one relay's contact carrier if the one it is mechanically interlocked to is already energized. This can prevent two mutually exclusive conditions from occurring inside an electrically controlled system's logic. One does not simultaneously go forward and reverse. Not only does this not make sense, it constitutes a phase-to-phase event in a three-phase AC electrical system, an event characterized by an arc flash hotter than the sun and a lab instructor whose anger is hotter than 10,000 suns. The mechanical interlock prevents this most heinous of actions from occurring. Now that we've got a good look at relay hardware and functionality, let us now discuss general specification of coils and relays and highlight some points of interest before we close up shop. Similar terminology is employed for contactors, so this might be a review if you already watched the contactor lecture. The rated voltage of a relay coil must be matched to the control system voltage. A coil designed to run on AC cannot be used on a DC system, even if the DC voltage is much lower. A coil presents both resistance and inductive impedance to an AC waveform because of the changing voltage waveform. A DC waveform only experiences the resistive component, and current draw will be exceptionally high and damage the coil. If one must interface two systems employing different voltage levels, for example, a programmable logic controller with a 24-volt DC output and a 120-volt AC relay coil, either one must exchange the programmable logic controller with one capable of supplying 120 volts AC output to directly operate the coil of the relay, or find a means of translating these two different voltage levels and flavors. Typically, such interaction occurs inside an interposing relay, basically a relay that translates one magnitude of input to a different level of output. We'll discuss both programmable logic controllers and interposing relays in later lectures. In addition to rated voltage, coils have a pickup, hold-in, and dropout voltage. A pickup voltage is the minimum amount of voltage necessary to overcome the at-rest spring or gravitational resistance of the armature. The hold-in voltage is the minimum voltage necessary for the coil to maintain the armature in the activated position once it has been activated. As can be expected, the hold-in voltage to maintain a position is a little less than the pickup voltage necessary to initiate movement to a new position. Finally, the dropout voltage is the amount of voltage below which the coil just returns the contacts to their deactivated state. AC coils are known to experience an inrush current at the moment they're energized, substantially greater than their sealed-in current once the armature has stabilized positions. Finally, given the coil's operating principle is that of magnetism, when current through it ceases, the magnetic field collapses in an effort to keep current traveling in the same direction. This sometimes results in a voltage spike that can damage equipment. Sometimes the means of suppressing this voltage spike is included internal to the coil or must be externally attached to it. As mentioned previously, DC coils with suppression means are polarity dependent. The mechanical linkages, springs, and contacts internal to the relay must be periodically inspected for proper operation and signs of mechanical wear. Misalignment of the contact carrier, spring, lever, or foreign obstructions will prevent movement of the contacts. Silver alloys typically form the conductive contacts because oxides of these alloys are also conductive. Closure of the contacts should ideally be as rapid as possible. However, contact bounce at closing can be problematic for the resolution of logical states inside the control system. It is for this reason some relay contacts are bifurcated or split down the center, minimizing bounce or chatter at closing. Similar to a contactor, the contacts of a relay have three typical ratings depending upon application: make, break, and continuous current carrying capacity. Inductive loads like motors experience an inrush current several times their normal current draw. Similarly, pilot devices like coils of contactors, other relays, and solenoid-controlled valves experience an inrush. Relays switching these loads must be sized to accommodate this phenomenon during closure and open. One last activity before we bring this lecture to a close. This is meant to be a thought experiment and test your knowledge of what we've thus far discussed. No calculator is necessary, only your consideration. Relays are part of the control aspect of a system. You should understand that when the coil of a relay is energized, the associated contacts change to their opposite state. As we'll learn in later lectures, the associated contacts, although physically part of the same relay, can be electrically all over the map. The coil for control relay 1 could be in the second rung of a ladder logic diagram, and the first set of associated contacts could be in the 7th rung, while the second set of associated contacts could be in the 15th rung. I'll show you some super handy organizational techniques in later lectures on ladder logic diagrams, but a simple technique in keeping your house clean is to assign a name to each associated contact based off the control relay. If control relay 1 has 2 associated contacts in use, the coil is called CR1. The first set of associated contacts is called CR1A, and the second set of associated contacts is called CR1B. You could also call them CR11 or CR12 or anything to distinguish them and make plainly evident that CR1 controls the states of these particular contacts. You'll see in later lectures, I sometimes go to the trouble of actually color-coding the coils and the associated contacts. Here's the conceptual exercise I'd like you to ponder. What if the signal used to energize a relay coil was delivered to the coil through one of the normally closed contacts associated with that relay? Can you predict what would happen? Think about it. No math, no calculations. Consider a relay with a coil designed to operate at 12 volts DC. What would happen if we took a 12 volt DC source and placed the normally closed portion of the CR1A contact in series with the CR1 coil? Would the coil energize? What would happen if the coil energized? What would the associated contacts do? What would happen to the associated contacts if the coil de-energized? Can you predict what would happen? 5, 4, 3, 2, 1. Here's what happens. You create a buzzer that will provide no end of mirth or annoyance to those in immediate proximity. why is the relay behaving in this manner? In its de-energized state, the normally closed contact allows current flow to the coil, and the coil is energized. When energized, the associated contacts change their opposite state, and the normally closed contact opens, de-energizing the coil. When the coil de-energizes, the normally closed contact returns to its deactivated state and energizes the coil. Repeat as necessary. You would not ordinarily wire a relay in this fashion unless you wanted to create a buzzer. However, I really get a kick about this particular activity because it directly highlights the relationship between and the function of a relay's coil and their associated contacts. You'll notice two important points about this activity. One, the repeated open and closure of the relay is occurring at a natural frequency, implying there is only so fast a device composed of moving parts can move. We'll learn in later lectures about solid-state relays, relays with no moving parts that can rapidly turn on and off at high frequencies, not limited by the physics of moving objects. 2. Notice the arcing that is occurring on the contacts. As mentioned previously, a coil contains magnetic energy. When current through it ceases, the magnetic field collapses, propels current in the same direction. This DC coil does not have any means of suppressing this arc. If this buzzer went on for any length of time, we'd damage the contacts. This wraps up our brief introduction to the relay. We'll be making use of this device in later lectures as the principal logical element of an electrically controlled system. Logical operations include, but are not limited to, controlling the motion, making decisions, and communicating information. We'll learn in later lectures how relays can make these logical functions possible. In conclusion, this lecture took a brief look at the relay. We identified the terminals, switches, contacts, and coils, and examined the functionality of a plug-in ice cube relay using a base and an industrial mini contactor relay. Additionally, we discussed general coil and relay specifications and had some fun making a buzzer out of a relay. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.